We're now going to continue working through examples to illustrate the method of undetermined coefficients. And we are up to number 3. And number 3, what I will do, I'll continue keeping our differential operator the same. So the y double prime minus 4y prime minus 12y. And now let's make the right hand side be a polynomial. So 2x cubed minus x plus 3, right? So just so that we see the full solution for the complementary function, so for y sub c, we have to solve the corresponding homogeneous equation, right? So we first solve it with a 0 on the right-hand side, and this goes back to our auxiliary equation. So m squared minus 4m minus 12 is equal to 0. This factors nicely. M minus 6 times m plus 2. So we got our two real distinct roots. So m1 is 6. m2 is negative 2. And then using the first version of our superposition principle, then the general solution of the homogeneous equation is c1 e to the 6x plus c2 e to the negative 2x. There we go, right? Now we have to think about an educated guess, right? So again, we're thinking of this as our differential operator. And what type of function would I have to put in this operator to get this output? So again, we're trying to work backwards here. So what is the input that would produce an output that's a polynomial? Well, if you think about it, it can't be any kind of trigonometric function. It can't be any kind of exponential function. It would have to be another polynomial. And if you think about it on basic algebra, it would have to be a polynomial of the same degree. So our educated guess for y sub p is, let me write it down. Now, what type of, like I said, it would have to be another third degree polynomial for us to get a third degree polynomial out. But when you look at this, there is the x squared term that's missing. So even though it is not a part of the output, it could possibly be a part of the input. It could just get eventually annihilated, right? It could have been eliminated, and we don't know. So when we're making an educated guess for our polynomials, if we have identified what the degree has to be, we have to write down the general form of that polynomial. So it would have to be some number times x cubed plus some number times x squared plus some number times x plus some number. So again, what is the general form of a third degree polynomial? It is this, where a, b, and c can be any real number. And what we want is, again, if we define this as our L, our differential operator, then we want L of this to be identical to 2x cubed minus x plus 3. But again, since we have several terms in our educated guess, right, what we think is the input for this problem, I'm going to go through and do the required derivatives individually. So I'm going to write down the first derivative, second derivative, then we essentially combine them all based on what our operator does. So the first derivative of our educated guess, using our power and sum rules from calculus, we get 3ax squared plus 2bx plus c. And then the second derivative, right, will give us 6ax plus 2b. And again, so it simplifies. So working with polynomials, as we might expect, each time you differentiate it, it's going to simplify the problem. So let's see how the algebra works out. So we require, so this is what we need. We want L of y sub p to be equal to the 2x cubed minus x, let me fix that x, so minus x plus 3. Well, what does L do? It's going to take the second derivative. So let's say you have your 6ax plus 2b. It's going to take your second derivative, and then it's going to minus 4 times your first derivative, which is 3ax squared plus 2bx plus c, and then it's going to minus 12 times your y sub p, your original guess, ax cubed plus bx squared plus cx plus d. And in fact, let me put the identical sign there. So we want these to be, or this to be, an identity. And again, before we go through the algebra, which might take a few steps, I just want to point out that even though we're making this as our educated guess, when we get to that particular solution, when we figure out the constants, one or more of these constants could be zero. We just don't know, right? So when we have a general idea of what the input would have to be, we have to keep it as general as possible and then work through the details. The algebra will work everything out, right? In algebra, we trust. So let's simplify. Now, as far as, well, let's not rush through it, right? Let's go through. Let's first drop and remove the parentheses. So we'll have negative 12ax squared and then negative 8bx minus 4c and then negative 12ax cubed minus 12bx squared minus 12cx minus 12d. And again, we want that to be identical to this, right? So what I want to do, the best thing to do is to write this, even though it's general and we have lots of letters, just like an alphabet soup, let's write this in the standard form. Just like how this is written in the standard form, let's do the same thing on the left. So let's write the negative 12a x cubed. That's the only term that has an x cubed. And if it helps, you can go ahead and just, sort of cross the ones out. Just that way, you know that it's been accounted for. Now let's look at the terms that have an x squared. We have two terms that have an x squared. We have a negative 12a x squared and a negative 12b x squared. So I'll write this as plus negative 12a minus 12b. That's times x squared, right? So we have that. So let's get rid of those two terms. So there and there. Now let's look at the terms that have an x. Now there are three terms that have an x. We have a 6a, a minus 8b, and a minus 12c. So I'll do plus, and then I'll do 6a minus 8b minus 12c, that quantity times x. And then so we got rid of the x terms. Those three terms are gone. And then we have, looks like we have just three terms that don't have a variable at all. So basically three constant terms. So then we have the quantity 2b minus 4c minus 12d, right? And again, we want this to be identical. Now what I'm going to do, even though when we write it, when a term has a coefficient of 0, we don't write the x term, but I'm going to write it in anyway. I'm going to say plus 0x squared and then minus x plus 3. And the thing is, since I have two identical polynomials of the same degree, the only way they can be identical is if the coefficients are the same. So this coefficient has to be equal to this coefficient. This coefficient has to be equal to this coefficient. This coefficient has to be equal to this coefficient, which is a -1. And then finally, this constant term, still called a coefficient, has to be equal to that coefficient, right? And so let's write down so it makes sense, since there are 4 letters that we're trying to solve for, A, B, C, D, it makes sense that we should have 4 equations, right? Because that's the only way we could possibly get a unique solution. So we have 12A is equal to 2. So that tells me that A is -1/6. Okay, good. First constant down. Then the second equation, and it looks like the way this linear system is going to work out is that we can essentially just continue to use, technically it's called a forward substitution, because you're starting with the first equation, then taking that information, going to the second, and so forth. We're used to doing a back substitution in linear algebra, but you have algorithms that are designed to go either forward or backwards, right? Depending on what form is optimal. But since I know what A is, I can then plug it in here, and I have -12 times -1/6 minus 12b. That's equal to 0. So this gives me a +2. Move it over, becomes a -2. So I have a -12b is equal to a -2. So therefore b is 1/6. And we keep going. Next equation is based on what I have in green. So 6a minus 8b minus 12c is equal to -1. Again, let's utilize what information we know. So 6 times -1/6, that's -1. -8 times 1/6, that's -4/3. And the c is what we're trying to figure out. So -12c, that's equal to -1. So -12c, the -1s cancel out, move over the 4/3, it becomes positive. So what do we end up with? So c is -1/9. Yep, looking good. And then finally, now for the fourth equation, the one that's defined by what I have in red, I don't need the a, because the a went away. There's no a in this expression, but just use what's there. So 2b minus 4c minus 12d has to be equal to 3. So 2 times 1/6, this is 1/3. Minus 4 times -1/9, that's 4/9. D is my unknown, so minus 12d is equal to 3. So let's see. All right, so if we get a common denominator of 9, so then this is 7/9, and then I have, okay, let's see here. So we have 3/9 plus 4/9 minus 12d is equal to 27/9. So then that gives me okay, so -12d is 20/9 dividing by -12, so d is -5/27. So d is -5/27. So there we go. We know what our input has to be to get this desired output. So our y sub p is equal to -1/6 times x cubed plus 1/6 times x squared minus 1/9 times x minus 5/27. So by the superposition position principal, the general solution. So the general solution of the nullity, we have to, again, I want it to be clear because, you're finding, oh, that looks like a mess. You're finding the general solution of the wholly in one case. Well, the end result of this process is finding the general solution of the nullity is, and again, the formula is y sub c plus y sub p, and y sub c is that familiar expression that we should know by heart now. But again, I'm using it just to kind of really emphasize that the second part of the process depends heavily on what's on the right-hand side, not what's on the left-hand side. Well, the left-hand side, the operator, of course, plays a role because it still has to operate on the input to produce the output that we want. But it's really that function on the right that starts the process with our educated guess. All right, so minus 5 over 27. So there's our general solution. And again, just to kind of hit home with the operator, if you pass this expression through our operator, it will annihilate, eliminate this term. So these two terms are in the kernel, right? And then this particular polynomial will produce the output that we wanted, that 2x cubed minus x plus 3. All right. Now, so it turns out there's a reason why these three examples that I chose, they involved functions on the right-hand side that were polynomials, trigonometric, and exponential. And when I say trigonometric, I mean sine and cosine. And exponential, you have like a e to the x or e to the 5x. These are the three types of functions to which the method of undetermined coefficient applies most readily. So if you have these types of functions on the right-hand side of the differential equation, right, the method of undetermined coefficients works best. So let's make a little note of that. So if the function on the right-hand side is of the following form. So let's try to write those down in a little bit more generally. So if you have something like a e to the k x, right? So that type of exponential, a cosine of kx, so that type of cosine function, or this type of sine function, like that, or they might be added together. So I'll say, like, if you have a cosine of kx plus little b sine of kx, if you have any of those, right? So these are the types of trigonometric functions that this method works well. And then finally, if you have some kind of polynomial, like an nth degree polynomial, so like a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 1 x and then plus a sub 0. And just remember that with to have a well-defined nth degree polynomial, this leading coefficient can't be 0, and of course your n is going to be some positive integer, right? So so I'll just use this notation, z for integer, and I'll just a little plus sign there for positive, right? So so if you have a function of this particular form, the method of undetermined coefficients works well, and it relies heavily on algebra, right? So the method of undetermined coefficients works well. So much so that now that we know, again, what types of functions work well with this method, we can actually say, okay, here is kind of a general rule or set of rules of thumb, right? Where if I see this kind of function on the right-hand side, this is my educated guess, right? So let's actually set up a table, again, based on what I have here, right? So if I call it, I think I call it's either F or G. I can never remember which letter I use on the right-hand side because there are so many different forms. But let's say it's F of X. And then over here, I'll just say my Y sub P. And then I'll put in parentheses educated guess. Right? Well, if your function looks like this, right? So if this is the type of output you want from the differential operator, then your educated guess is going to be something like this, right? Again, it would have to be the same type of exponential. We just don't know what the coefficient is. And that's why I am changing the coefficients here, right? So I'm going to use the uppercase as the ones that we don't know, and then we have our process for going through. And now if you have any of these, so I'll kind of group these. So if you have a cosine of kx, a sine of kx, or a cosine kx plus b sine of kx, all of these, whether you have just a cosine, just a sine, or a linear combination of the two, then your guess has to be a linear combination of the two, right? Again, it's just that it's that unique relationship between sine and cosine that just seem to be tied together. It's like they're tied together at the hip or something, right? They always go together. And there we go. And then if you have your nth degree polynomial, so I'll just write it. If you have your nth degree polynomial, then your educated guess is going to be basically, yeah, like a big A. Now, again, because I don't know how many terms, I'm just going to do this, and then you'll have your x to the n, and then you'll have your a sub n minus 1, x to the n minus 1, all the way down to a sub 1, x plus a sub 0. So again, you make an educated guess that contains all the terms, right? The general form of that nth degree polynomial, right? Now, the interesting thing is, there are some times where that function, right, your output isn't just of one type. What if are you allowed to combine them? Could you add an exponential and a trig, or multiply an exponential by a polynomial? Yes. So I'll just say, note, f of x may contain the sum, difference, and or product of these types, right? So of these types of functions, not quotients, because when you divide them, you lose the pattern that we have. If you think about it, once you start dividing functions and then have to differentiate them, it gets a lot more complicated. So what your f of x, I'd say in the most extreme form, your f of x could contain any sum, any finite sum, any finite difference, any finite product of these functions. Right? But I'll emphasize, but not quotients, right? If let me put it this way, if your function is, let's say, a polynomial divided by an exponential, then what that means is you cannot use this particular method, right? So in this method, you need functions that are easily differentiated, and not only that, but when you differentiate them, the type of function, it stays the same. Repeated differentiation of an exponential like this produces another exponential. Repeated differentiation of a function of these type, all three together, will produce another function of the same type. And repeated differentiation of a polynomial will produce another polynomial. Yes, the degree will be different, but it will still be a polynomial, right? So to illustrate this, let's end with an example that involves a different differential operator, right? And a sum difference type thing. All right, here is our example. So again, I'm just going to write down the nullity, and then we're going to find the general solution. So let's say we have y double prime plus 4y is equal to, and then we have 3x times e to the 2x. All right. So definitely it's a non-homogeneous one, so it requires a bit more work. So let's start with our complementary function. So for y sub c, we're going to solve the corresponding whole-d. So that's y double prime plus 4y is equal to 0. So the auxiliary equation in this case is m squared plus 4 is equal to 0. And you can either work through the quadratic equation, or if you're a little bit more comfortable with complex numbers, you'll see that m here is plus or minus 2i. So this is now actually case 3. And here our alpha is 0 and beta is 2. So therefore y sub c is that e to the, and I'll write it in the factored form, e to the alpha x times cosine of beta x, well, I forgot my c1, and then plus c2 sine of beta x. So there we go. Obviously, with an alpha being equal to 0, then the e to the 0 here is 1. So our complementary function simplifies to c1 cosine of 2x plus c2 sine of 2x, right? So there's our y sub c. Now, when we look at our function here, or function on the right-hand side, the output that we want, right? It's actually made up of the product of two types of functions, because this factor here is a linear, this is a first degree polynomial, and then this factor here is obviously exponential, and it's a product. So what we're allowed to do in our guess is to say that, yeah, our general guess would have to have, instead of just having a constant times the exponential, I would have to have the general first degree polynomial times the exponential. So based on 3x e to the 2x, our educated guess of, or for y sub p is this. So we're going to say that our y sub p would have to be of the form. So again, what does the general first degree polynomial look like? Well, it's the ax plus b, and then that would multiply my e to the 2x, right? So the modification here is, because there is now an as a part of the coefficient of the exponential, I have to interpret this as a first degree polynomial times an exponential function, and then that gives me the guess, right? So once we do this, we're going to go through now the differential operator. It does not include y prime, but unfortunately we can't just go from y to y double prime. So we'll still have to find the first derivative and then the second derivative. The other thing too that adds to this when you start combining the different types, especially with multiplying, is that when you differentiate, you may end up using the product rule. So we got to remember our product rule here. So the derivative of ax plus b is a, and then that's times the exponential, and then plus the linear factor times the derivative of the exponential, which is 2e to the 2x. Now, what I like to do when I differentiate these types of products where one of the factors is exponential and the other one, let's say, is polynomial, and it also works for sine and cosine, I always like to try to factor if I have to differentiate again. So I'm going to factor out the e to the 2x, so kind of keep the exponential by itself and then keep everything else inside. Well, what do we have inside? We have an a, and then plus we have this 2 that will multiply that factor. So that's 2ax plus 2b, right? So that's what it looks like. And we have to differentiate again, right? And so I'll give myself a little bit more room. Now the second derivative, again, we're going to use our product rule. So the derivative of what I have in parentheses is just 2a, because these constants will go away. So I'll have 2a times the same exponential, and then plus, I'll rewrite this so that it's in that linear pattern. So 2ax, and then plus a plus 2b. And then again, when I differentiate the e, I'll get 2e to the 2x. And yet again, let me go ahead and factor. So if I take out a e to the 2x, what do we have left? So we have a 2a there. And then take this 2 again and double everything inside of this parentheses. So I have plus 4ax plus 2a plus 4b, right? So that's our first and second derivatives. Now the operator just takes the second derivative and adds 4 to the original. So at least that expression isn't going to be too bad, right? So our operator of our educated guess, it's going to take the second derivative. So it's going to take the quantity 2a plus 4ax plus 2a plus 4b times e to the 2x, and then it's going to take plus 4 times my original guess, which is this. Ax plus b, and then times e to the 2x, right? So that's what the operator does. And what I'm going to do, once again, is factor out the e, right? Because you'll always have, because if you start with a product that involves an e to the 2x, every other derivative or every combination of those, of your function and your derivatives, will always have factors of e to the 2x, right? So let's see. So we have all of this together. Now, what I didn't do, I could have started to combine some like terms. So let's go ahead and do that. I'll write the 4ax plus 4ax first, and then plus 4a, and then plus 4b. So that's this part. And then here, distribute the 4. So I have another 4ax and 4b. And then that's all times the e to the 2x, right? So again, simplifying this. So we have a total of 8ax and then plus 4a plus 8 b times e to the 2x, right? So what does this tell me? Well, this tells me that, so remember what we want this to be our output. So this implies we want 8ax plus 4a plus 8b times the quantity e to the 2x. We want that to be identical to our output of 3x e to the 2x. So the only way that will work is this. Let me write this in another form. This is the same as the quantity 3x plus 0 times e to the 2x. So if I match up the coefficients, definitely see the e is already there, right? The coefficient of the x here would have to be equal to this coefficient of x. And then the constant terms here, the 4a plus 8b, well, I don't want any constant terms here in my output, so it would have to be equal to 0. So we want these terms to be essentially annihilated. How do we get that? Well, we set up our system. So 8a equals 3. That means a is 3/8, right? And then we want 4a plus 8b to be equal to 0. Well, I know what a is. 4 times 3/8, that's 3 halves. Oh, I said halves and I wrote the eighth. Right, there we go. And then plus 8b is equal to 0. Solving this, so subtracting 3 over 2, so that's negative 3 over 2 dividing by 8, so b is negative 3/16, right? So that tells me what my y sub p is. So therefore, the input that will produce the output based on this differential operator is the function 3/8x minus 3/16 times e to the 2x. And therefore, here's our general solution. Again, using the superposition principle, so the general solution is y equals y sub c plus y sub p. Y sub c was that, remember with our complex conjugate roots, we got c1 cosine of 2x plus c2 sine of 2x, and then plus our educated guess here. So 3/8 x minus 3/16 times e to the 2x. And there we go. So you can see once you start combining different functions, especially with products, the product rule, having to repeatedly differentiate, not difficult, but it is tedious. So you have a lot more terms to keep track of. And this is a good example of such a problem. Not a very complicated function on the right-hand side. It's just, it looks fairly innocent. But again, we have to interpret that 3x as a first-degree polynomial. So our guess became this, which led us to, ta-da, this. All right. Okay. So, and this story is still to be continued. So tune in for the exciting conclusion to our 3-part mini series of the method of undetermined coefficients. See you then.